Uh, Today's talk is going to be quite different from the rest that you've seen thus far. And there have been some really interesting talks. I've really enjoyed it. Um, and this is really a story of serendipity where we started out 23 years ago on a collaboration with industry, trying to make hyperbranch materials in a one-pot approach using reaction of A2 and B3 monomers, which is quite now a proven strategy to make hyperbranch polymers. We were trying to make hyperbranch polyurethanes for the end use of hot melt adhesives. But what we found ourselves making was a completely different set of materials. Um, And when Alex Clark, the MSc student who was working in my lab, um, he was very, very diligent, and he realised that he's made something quite unusual. So the top structure, let me just see if I can get the laser pointer. Spotlight, no, I can't seem to find the laser pointer. Apologies. Oh, here we go. No, I haven't managed to find it. So the structure in red, he managed to isolate this material. It's got a molecular weight of just over 600, but it didn't behave like a relatively small molecular weight material. It behaved very much like a polymeric gel, and that compound is in the left-hand vial, sort of the creamy-coloured compound. And when he turned the vial on its side, so that's with all the solvent removed, he realized that that material just simply didn't flow at ambient temperature. And you had to heat it above 50 degrees to get that material to flow. So since my group is focused on synthetic polymer chemistry, we made some modifications and we took away the alcohol groups and replaced them with butyl chains there in the blue structure. And that's the compound in the right-hand vial in all of the three photos. And when you turn that material on its side, that vial on its side, the material flows at ambient temperature. So it has very different properties to that of the compound, which is not too dissimilar from it structurally. And we did a lot of spectroscopic analysis, and what we worked out from mainly IR analysis, detailed IR and NMR analysis, was that this material sorry, my computer appears to have locked up on me. Apologies. Excuse me, I'm gonna have to stop sharing and start again. Can you still see that?
Not yet.
Okay, I'll have to stop sharing. Has that come through now?
Nope. Oh, yep.
Thank you. Right, I'll try again. Okay, now we can advance. So apologies about that. So what we worked out was that these materials here were assembling into a completely random network where the molecules are held together by lots and lots of different weak non-covalent interactions. And we wanted to use this more advantageously for the application of hot melt adhesives. And so we turn to the field of supramolecular polymers. And this has taken us down a 20-year journey or so, where we've learnt a lot about these dynamic materials and how very small structural changes can make a huge difference to the physical properties of these materials. And shown here is a diagram based on that produced by Stuart Rowan about 20 years ago, whereby the little semicircular red structures represent the supramolecular recognition units, which can, when appended to a linear polymer, can assemble via non-covalent interactions. And also, if the polymer is of the right polarity, you can actually get phase separation occurring, whereby the supramolecular aggregates start to assemble into distinct regions. But as a consequence of the weak non-covalent interactions, you can readily disassemble these networks. So with this in mind, the simple polymer model that we've been working on for the past 20 years or so is based upon this simple structure here, whereby we have a polymeric unit in the middle, which is coupled via urethane linkages to end group functionalities, which can either be coupled via urethanes or ureas or other appropriate polar entities to create these structures which have apolar and polar characteristics. The synthesis is relatively simple and scalable. We can make these materials in hundreds of grams scale now, where you take a polymeric dial and you can vary the polymeric dial readily. You react it with a diisocyanate. I'm showing you here for MDI, a very commonly used diisocyanate in polyurethane chemistry and adhesive technologies. And by using the appropriate stoichiometry of the diisocyanate to your dial, you can end cap the polyol with isocyanate units, which is still reactive. Then by judicious use of an appropriate nucleophile, you can then end cap that diisocyanate precursor, which will be reasonably chain extended, but we can control that by the monomer feed to afford the desired supramolecular polymers shown at the bottom in red. And we've primarily played around with either alcohol or amine nucleophiles to generate urethane or urea end groups. Now, the properties of these materials, from the pre-polymer to the desired polyurethane, are quite dramatic. So the pre-polymers tend to be quite thick, viscous oils, which aren't always the easiest to process, if I'm being honest. But once you've end capped them and you produce materials which are elastomeric in character, and shown here is just one of the derivatives we've made, which has 2 urea end groups and alcohol amine chain ends. And that material is a really nice adhesive. And you can see a simple peel test being done at the top. And these are elastomeric in nature, as you can see by sort of the Phil Woodward's hand holding the little strip of an elastic band there. So once you've made your pre-polymer, you really can vary the structure of your materials quite dramatically and control those structures such that you can change the polymer by only a couple of atoms. So shown on the left-hand column are the urethane series that we've developed with a range of different polymer mid-blocks, polypropylene glycol, polyisobutylene, and the polybutadiene derivatives shown below, with either alcohol end groups or alkyl end groups. But if we alter the nucleophile in the last stage of the reaction sequence that I showed you to an amine, we can make the urea derivatives. So we have comparable materials in terms of molecular weight and molecular composition, all bar the change of a urethane end group to a urea end group. So we're literally changing an oxygen for an NH in the corresponding ureas. And that enables us to do a lot of molecular engineering and dive deeper into structure property relationships. So typically the way that we have studied these materials is using rheology. And the way that we've studied the rheology is typically as a temperature sweep, because that is most relevant to the use of these materials as hot melt adhesives. And what the industrial sponsors were interested in were having materials which had very distinct thermal transitions within very narrow temperature ranges, such that you could melt and cool and go from fluid to solid very, very quickly. And that's typically what you require from a hot melt adhesive. When we analysed these supramolecular polymers via rheology, what we quickly realised was that these materials have some very interesting characteristics. Now, we're never going to really use a hot melt adhesive below zero, but since we were able to, with the rheometer, we're able to study below zero, we studied these compounds across the temperature range shown from below -50 up to 150. And what you can see is that for the polyurethanes shown in blue, which is the diol end group, the butyl in the pink, and simply end capped with methanol in the more tan color there, is that you have very different rheological characteristics. But these materials are behaving like block copolymers, where there's a polymer sort of glassy state below zero, but as you increase the temperature, you simply don't get complete flow directly. You have this rubbery state where the rheological characteristics are maintained in terms of the storage modulus. And so this is characteristic of a block copolymer behavior, and it indicates that there's quite a reasonable degree of organization within these materials in the bulk state. And I'll talk about that in a bit more detail in a few slides' time. Varying the polymer block really did dramatically affect the rheological characteristics. If you have a relatively polar polymer block, such as PPG shown in light green, that second rubbery transition is really very shallow, and the material flow goes into liquid flow very, very quickly. Whereas if you have apolar mid-blocks, such as polyethylene cobutylene shown in cyan, or the polyisobutylene shown in dark blue, you can see how that rubbery transition is extended beyond 50 degrees C and relatively level before it starts to enter the viscous domain above 75 degrees. So to have a stronger phase separated material, you really need to have a more apolar mid-block. Now, I talked about the ability to modify the structures in terms of urethane and urea end groups and look at the effect of simply changing a couple of atoms between comparable polymers. And shown here is the rheological profiles for the urethane and urea derivatives using the ethylene cobutylene mid-block, one of the more apolar systems to give stronger phase separation. And what you can see is that as we increase the polarity of the end group from a urethane to a urea, you actually extend that, the duration thermally of that rubbery phase. So you have a stiffer material over a longer temperature range. And that is simply due to the ureas hydrogen bonding. Ureas are known to stack via bifurcated hydrogen bonds, and that's what we think is happening here. So very, very small molecular changes in these supramolecular polymers has very drastic effects on the mechanical properties. And these materials are similar to those that have been reported by other groups such as Meyer and Zimmerman are excellent examples, but their systems have highly pre-organized, extremely strongly hydrogen bonding end groups with dimerization constants for the association of the end groups up to 10 to the 7 reciprocal molar. Whereas these systems here are far weaker in nature. And so what we believe is happening with our systems is rather than having very distinct hydrogen bonded assemblies, we're creating very loosely associating domains of our polar end groups where there's lots and lots of different hydrogen bonding combinations occurring in the polar end groups. Now, we're pretty confident that we have phase separation occurring as a consequence of some Sachs analysis that we did, where we see that we have irregular morphologies that quite broad Sachs peaks, indicating domain spaces ranging between 6 to 8 nanometers. And what was interesting was that we were able to correlate the intensity of those Q bands with the hydrogen bonding strength of the end groups, where the most intense end groups, associating end groups, have the most intense Q bands. Now, what was also useful in terms of the hot melt adhesives was to look at their thermal properties. And so we did variable temperature Sachs analysis across a 140-degree temperature range. And what we could see was that we could thermally cycle these materials reliably. There was no degradation across the temperature range that we studied. And this kind of led us to another area, which kind of leads us into a field where we're trying to actually extend the lifetime of polymers, and it directly addresses one of the main points that came out of the previous talk in terms of how humans use polymers and how we should be mindful of how they degrade. Now, the other thing that we've done, again, with our synthetic hats on, is we've varied the end groups. And if we increase the hydrogen bond density by having two sets of ureas separated by a benzene ring, we have a very strong hydrogen bond association, which we can see through the aggregates indicated by TEM. But what we also are quite clear is that the materials are shown by this shear storage modulus in the top right, is that the materials, when you have stronger hydrogen bonds, which are more pre-organized, their rheological characteristics are very, very different. So we don't tend to see across the temperature range that we've studied before, this fall away into the viscous domain. But as a consequence of that, the materials are far stiffer, but not as elastic in nature. So again, with polymers, if you make them stiffer, they tend to be elastomeric. If you make them more elastomeric, they tend to be less stiff. We've also varied the diisocyanate, and this was a collaboration with Cristina Prizicario's group from Romania, where her group had been working with a diisocyanate. Instead of a methylene bridge between the two phenol rings, there was an ethylene bridge, and that allowed for flexibility of that group to enable more efficient hydrogen bonding. And that's mapped out directly in terms of how these materials assemble and their mechanical properties. Where we have far stiffer materials, there's an order of magnitude increase in the storage modulus in comparison to the previous systems that I showed you. So the reversible thermal characteristics led us in 2008 to collaborate with Howard Colquhoun's group and Stuart Rowan's group in America in the area of supramolecular healable materials, where we can use the dynamic association of the hydrogen bonds and the relative weakness in comparison to a covalent bond to have network materials which you can break and anneal in order to heal them. And that's as a consequence of this weak associations of these hydrogen bonding groups. So working with materials very similar to what I've shown you before, ethylene cobutylene systems with urethane end groups, we were able, in collaboration with Clive Sivier's group at Oxford, to study the mechanical properties of these materials. And shown on the right-hand side is the images of how these materials heal at body temperature around 37 degrees C. And the profilometry plot at the bottom right-hand corner of this slide shows you that after healing for a little over 2 hours, we've reattained the damaged zone has been repaired. And so the way that we do that is that we take our film, we cut it, we put the two ends in close proximity, and then we thermally anneal them, and we study that by microscopy, and those are the images that we've shown you there. Now, these materials were also really nice adhesives, and what we've shown here is the polymer in the photograph A. You can see the polymer, a rectangle, and it's actually adhered onto a pigskin. And in the middle there, indicated by the black lines, there's a very, very faint line, which is where we've cut our polymer with a scalpel. Then we've exposed that to 37 degrees C, and you can see that the pork skin slightly cooked slightly. There's a little bit of creep with our material as well, but you can see the image in B and E of the damage zone where the valley has simply filled up, and that's also indicated by the profilometry plot, where we've run the profilometer across the surface, and we can't detect a valley of any great note. Now, we've played around with the end groups with healable materials as well, and this is some excellent work done by one of my PhD students, Alakam Tarek, where he's tried to increase the thermal processing of these polyurethanes by appending aliphatic amide groups at the end, and shown here are several that we've made. And these are phase-separated materials, as indicated by the AFM images, and the optical microscopy images reveal that it takes us up to over 200 degrees C to heal this material, and that's as a consequence of the elevated or the stronger associations afforded to us by the polyamide end groups of these materials. Now, I'll just finish off by showing you that actually making pure materials, as we've spent 20 years trying to do, isn't always actually the best way to produce materials with the best properties. So what we've typically done is we've taken our polymeric diols, reacted them with the diisocyanates, and then end capped them, and then precipitated and purified our polymer, knowing full well that we're removing a low molecular weight bisurea if we use amines, or bisurethane if we use diols as a nucleophile. But one of my PhD students didn't do that. She simply just took the raw material and studied it. And she varied the monomer feed such that we could actually adjust the loading of that relatively low molecular weight component. And so what we were trying to do was to see if these low molecular weight components would actually enhance the phase separation and reinforce the supramolecular polyurethane. Well, obviously they did, otherwise I wouldn't be telling you that. And what we've found is that you can actually get quite significant enhancements in the storage modulus by simply retaining that low molecular weight additive within that within the bulk polymer, but it comes at a consequence of you increase the Young's modulus, but you tend to lose out in terms of their elastic characteristics. But these materials are also healable. At 90 degrees C, you've healed the material completely. So that comes to the end of my talk. Apologies for the technical glitch at the beginning. But hopefully what I've shown you is that by appropriate modification of these supramolecular polymers, we can actually modify their properties quite dramatically. And it doesn't necessarily take especially dramatic structural changes to have a really effective change in the mechanical properties. And finally, I'd just like to thank all the people that I've collaborated with and the past and present research group members who have done all the hard work for me, and also the sponsors who have sponsored it.